Hi and welcome to another video lesson of this course, finite difference methods. And today we'll be discussing the two-dimensional lid-driven cavity, starting with the derivations and some theoretical explanations. Okay, so there should not be anything that's not familiar now except for the pressure gradient term in this particular equation. So what we have here is the u momentum equation, in which we have the time derivative, the convection term, the pressure gradient, and the diffusion term. And we can also write a similar set of equations for the v momentum, and we have the again the time derivative, convection, pressure gradient with respect to y direction, and the diffusion term. One more equation is needed to solve for the two lid-driven cavity, is the Poisson's equation, in which we have a source term, but this source term is more complex than what we did in the last tutorial. So the source term is basically uh, the negative of rho multiplied by the gradient of u with respect to x plus 2 times the gradient of u divided by v, and the gradient of v with respect to x, and the gradient of v velocity with respect to y itself. So one thing we should understand is how did we get to that equation. It's not explained a lot in most of the stuff that I see, so I decided to go ahead and explain it. Hopefully how did we end up there with that particular source term. So it's kind of like a combination, or how to combine these equations together using that source term. Okay, so initially in Navier-Stokes equations, we have the continuity equation for the that saying that the divergence of the velocity is equal to 0, and then we have the momentum equations. So what we do is, first we take the divergence of equation 2 and equation 3, namely the two momentum equations. First, for the u momentum equation, we take the divergence with respect to x, so dou by dou x. Simply it means introducing dou by dou x for every single term. So if we introduce, for example, dou u by dou t, we have a dou by dou x term here. For the terms with two velocity components, namely, for example here, this particular term, we have u as one term and dou u by dou x as one term. So if we take that, we end up with two terms, which is dou u by dou x, dou u by dou x, and the other term where we have u separately and dou by dou x of dou u by dx, dou x. And similarly for the left hand side v, we can do similar kind of thing. So dou v by dou x, and the term that appears here, dou u by dou y, and then take v separately, and then take the divergence of the inner term, so dou by dou x of dou u by dy. So spend some time and think about this particular derivation. So I'll explain it one more time just to make it clear. So we take the dou by dou x of every term in this left hand side. So dou by dou x multiplied by the first term, dou u by dou t, and here we have the u term, so ignore this term first, and then we introduce dou by dou x of u, so dou by dou x of u, and then take the second term as it is, and then for the next step, leave this term as it is, and then introduce dou by dou x of dou u by dou x. So, if for the terms having two separate variables, you take one each and then introduce a dou by dou x of that term. Similarly, for the uh, v momentum equation, we can take by with respect to y direction, so dou by dou y of dou v by dou t, and then take dou by dou y of u first, and then keep this term same, and then in the second one keep the first term same, and then take dou by dou y of the second term, and we end up with the full set of divergence equations. And moving on, now it's time for us to rearrange. And upon rearrangement, so this is initially how it looked like. Dou by dou x of dou u by dt remains the same. So dou u by dou x twice, which is coming from here. So we have dou u by dou x twice. So it becomes a squared term. And this particular term, when combined, become dou squared u by dou x squared, and this term becomes multiplied together dou v dou u divided by dou x dou y, plus again we have the v velocity and dou squared u by dou x dy. So that's the combination or the rearrangement for left hand side 2, momentum equation 2, for the u velocity, and we do similarly for the third one, which is the momentum equation in y direction. So upon rearrangement we get this particular one. So just the time derivative remains the same. This term is combined together. This term becomes dou squared v by dou x dou y, and this term can be combined together as a squared term, and this term become v multiplied by dou squared v divided by dou y squared. Okay, so now we add them together, left hand side 2, which we just rearranged, we add them together, and this way we end up with taking the dou by dou t outside, and this dou u by dou x plus the dou v by dou y plus this term dou squared u by dx squared plus this term here dou v du by dx dy plus this term, the first term in the left hand side 2, plus this term here in green, and then these two terms in blue and black, and the last two terms here. So I have color coded them just to make it easier. So similar terms are in for example, the black are the terms in the black are similar in their structure, and these two terms are similar as well, and these two terms are kind of similar, and these two terms are kind of similar. Okay, so here I'm explaining how we can come up to this particular uh, derivation. So if you have u multiplied by, so it's this term here, dou squared u by dou x squared, then also you have another term u multiplied by dou squared v over dou x dy. So it's these two green terms here. You can take the common u outside, and you can take the common dou by dou x outside, and you end up in the bracket with a term known as the divergence term. So these two end up as the divergence term for in here, and these two in kind of orange, is it, or pink color, end up also as a divergence term when you take common factor outside. So to summarize, from here, when we do this step, this particular step, we can shorten this equation by saying that this these two green terms become a singular term, and these two pink terms become this term, and the derivation is here. Okay, so I recommend that you try this on your own as well. Otherwise, even if I explain here uh, too many times, it wouldn't be easy to understand. It's just better if you would write it down and try it for yourself. This is just the left hand side, and that's not done yet. We still have to take the we still have a couple of more steps. So in deriving this particular equation, we say that the divergence field must be 0. So we can cancel out these terms. So here I have a divergence term, here I have a divergence term, and here I have a divergence term. So we end up with 0 term here, 0 term here, and a 0 term here. Okay, again, so we to come up with the source term for the Poisson equation, we say that the divergence of the velocity field must be 0. It may not be exactly 0 in a numerical domain, but in a continuous domain it is. And to ensure that, we are saying that the divergence should be 0, and therefore we should be able to cancel out these terms, because if the divergence is 0, 0 multiplied by anything is 0, simple as that. And therefore we end up with this equation, dou by dou t of, sorry, no, not dou by dou t, dou squared u by dou x squared, plus these two terms are similar in each other, so they can be combined together to multiplied by a 2, and we are left with dou v squared by d dou v by d dou y squared. Sorry about that. So dou squared u by dou x squared plus 2 times this term, and dou v squared by dou v by dou y squared. Alright, so now this should look familiar. It is the source term on the right hand side of the Poisson equation, and that's how we ended up there. On the left hand side, sorry, on the right hand side, we have the of the momentum equations. We have two terms, three terms, basically the pressure gradient and the diffusion terms for the u momentum and for the v momentum. So let's actually go back there and just visualize this before we move forward. So what I'm talking about, we've done the left hand side for this equation 2 and equation 3, and now we are moving on to the right hand side. Okay, so on the right hand side, upon taking the divergence operator, because we just can't take the divergence of left hand side and stop there, we need to do similar for everything else. So upon taking the divergence, this has, for example, in the right hand side 2 for the second equation, this changes to a dou squared p by dou x squared term, and this changes to dou cube because it's already squared terms, and when you multiply it becomes dou cube u by dou x squared plus dou cube u by dou x dou y squared. So the derivation is really simple here for the right hand side. Similarly, for the right hand side 3, we can do the same thing. So we have come up with two particular ones, and now we add them together and we end up with this equation called minus 1 over, because I forgot to, actually I have forgotten to put this minus sign here. Nevertheless, the pressure gradient is a minus term, and then we add dou squared p dou x squared plus dou squared p dou y squared, and then add all these terms together. You don't have to do anything else yet, just add these four terms together and take the common term nu, which is the viscosity outside, and we end up with this particular equation. So if we now take dou squared by dou x squared outside, we are left again with the divergence term. Should be fairly straightforward. So we have here dou cube u by dou x squared plus dou cube u by dou x dou y squared, and we take dou x squared as the common factor outside, and what we are left with is the divergence term for these two terms and for these two terms. And again we enforce the divergence conditions. uh, 1 second. We say that the divergence field must be 0, and therefore we are left with just this particular pressure term, and that's the end of the derivation for the right hand side. So now if we look back at the beginning of our equations from here, we see that this is what we derived just now on the right hand side of these equations, momentum equations, and this is what we derived for the left hand side, and that's how we end up with the pressure Poisson equation for using the continuity equation and enforcing that the divergence field must be 0, and uh, we end up with these equations. Hope you understood that. Thank you.